All right, how you doing? We're going to look at the dual nature of light. We're going to relate speed, wavelength, and frequency. We have two equations. You need a calculator. All right, so I'm going to go ahead and share my screen with my iPad here. And we're going to title these notes the dual nature of light. So go ahead and start writing that. Dual nature of light. And here we are. Dual nature of light. Okay. Let's go ahead and get to this. So light, we're going to relate electrons, movement of electrons to light, but today we're just going to look at light, okay? He's got two behaviors, light as a wave and light as a particle. Okay, very two opposing ideas. A wave, as you know, is somewhat like this, right? And a particle, as you know, is more like this, right? This is continuous, as it doesn't begin and end. And this is discrete, which means discontinuous. Oops, wrong spelling. Discontinuous. It means it begins and it ends, right? There's one there, it ends. There's one there, there's one there, there's one there, as the wave is continuous, all right? So hopefully you see that. We can talk as light as a wave because it has both wavelengths and frequencies, all right? Right? And we can look at the electromagnetic spectrum, right? And what is it a spectrum of? It's a spectrum of radiation. And it organizes the different type of radiation. And realize here, guys, that the word light and radiation, light is a form of radiation, right? Light waves are called radiation, okay? So we have different forms of light waves, okay? And we organize them in the electromagnetic spectrum. We can start over here where our waves are far apart and we have a low frequency, and we can try to bring them together. I'm not very good at it, right? So you can kind of see what I'm getting at, I hope. Far apart versus close together. Here I see they're very far apart, so I have a high wavelength, right? And over here, the waves are pretty close together, so I have what's called a low wavelength, all right? And over here where I have my high wavelength, I have a very low frequency. I have a low occurrence of the wave repeating itself. So I call this a low frequency. And over here where I have a low wavelength, where they're very close together and they repeat themselves quickly, we have what's called a high frequency. They're very frequently repeating themselves, right? So I'm gonna write high frequency, all right? So let's see, high frequency is here where we're fast, and our low frequency, right, is going to be over here where it's spread out, all right? And you could easily see how this would be the low energy side. Everything seems to be moving more slowly, right? And this is the high energy side where everything is moving more quickly. And we could name these, right? We've already learned that way over here where we have high energy, we'd call that gamma. And next to gamma, we would have our X-rays, right? Next to our X-rays, we have our UV radiation, ultraviolet. We then have the part that we can see, which is that visible light spectrum. We have what? Infrared. And then we have our radio waves. And over here, we have our microwaves. I think I have those in the right order. And you know that if the, oops, let me not have that big thing. If the radiation falls somewhere within this in terms of its wavelength and its frequency, if it falls in this range, then our eyes can see this, right? And that's where our colors come in. And our eyes, red, orange, oops, I forgot my yellow. Our eyes can see radiation that has wavelengths, frequencies, or energies that fall within this range, right? If they're between these values here, then our eyes can see them. There's all these others going on around us, but our eyes cannot pick up those wavelengths and frequencies, okay? Now we can quantify, we can talk about these values numerically, right? And we can use our speed equation. And we can say that the speed of what? Of radiation, of what's radiation? It's light, is equal to the wavelength of that radiation multiplied by the frequency of that radiation. All right, let's give these some symbols. This is C equals wavelength times frequency, or frequency. You see it both ways, both of those being frequency. Okay, so we have speed equals wavelength times frequency. The speed of radiation, the speed of light, is a constant. The speed of light is 3.00 times 10 to the 8th meters per second. The wavelength must be measured in meters because, as you see, our speed has a distance in terms of meters, so our wavelength must be in meters, and our frequency must be in terms of per second, which is the same as a hertz, or a per second. Okay, and you can see why, because here we have a per second and our speed, so our frequency must be a per second. When you go to write your answers into your Google form, you want to use per second as such, so it's calculated correctly. But all of these here mean the same thing. They all stand for per second. Hertz is a per second, S negative means per second, and /S means per second. Let's look at an example. Okay. Calculate frequency if wavelength, kind of keep these words to a minute, wavelength of what? Radiation is 802 nanometers. Okay, so let's write this down. It says calculate the frequency if the wavelength is 802 nanometers. Then I know that there's an equation as such which relates these two variables. I need to solve for my frequency. So I will divide both sides by my wavelength. Doing algebra, this will cancel. And I'm left with frequency equals speed over wavelength. Okay. I know the speed. Remember that the speed is 3.00 times 10 to the 8th meters per second. And the wavelength right here is given to me at 802 nanometers, right? I already wrote that down, being a little redundant here. Now, once again, hopefully you're seeing that this is in meters. Therefore, this must also be meters. So I need to utilize my T-chart that we learned, and we will convert nanometers to meters. This is the metric system. Which one is bigger? Meters, give it a 1. How many times bigger? 1 times 10 to the 9th. Divide, we get 8.02 times 10 to the negative 7th meters. So I'm going to plug everything into my equation, and I'm going to solve for my frequency. Frequency equals speed over wavelength. The speed is equal to 3.00 times 10 to the 8 meters per second. And the wavelength is 8.02 times 10 to the negative 7th meters. I see that my meters will cancel. My answer will be per second. And I'm going to have 3 significant figures in my answer. I encourage you to put this in your calculator to make sure that you're doing your exponents correctly. Otherwise, you will get the wrong answer. So right now, you should be putting it in your calculator, and you should check to see that you, in fact, get 3.74 times 10 to the 14th. Does that make sense? Yes, 8 minus negative 7 is 8 plus 7, that's 15. Move the decimal, we end up with 14. And this is our frequency. Okay? They gave us nanometers, we had to convert that. All right. What is the wavelength if the frequency is 98.5 megahertz, right? That's like a radio station, 98.5. Okay, what is the wavelength? Wavelength equals question mark. If the frequency, I'm gonna use the letter F, so I don't, maybe that will, if the frequency is 98.5 megahertz, okay, well, we know that the speed equals the wavelength times the frequency. If I divide both sides by the frequency, then I can isolate my wavelength, and I end up with wavelength equals speed over frequency. I know that the speed is 3.00 times 10 to the 8th meters per second, because we're talking about light and it always travels at that speed. Okay. And I know that my unit here, is in per second, which is a hertz. However, this is a megahertz. So I will have to convert that utilizing our T-chart and the metric system. I will put megahertz here. I will put hertz here. And I will say that I will say which one is larger. I was about to make a mistake. The megahertz. And I will say how many times larger. I will then multiply those values, and I'll end up with 9.85 times 10 to the 7th hertz. Okay, and that is my frequency. So I'll put it down here, 9.85 times 10 to the 7th. I'm going to write hertz as per second, and I see that those will cancel, right? That's why we had to convert it. I'll be left with meters. And I'm going to put this in my calculator, and you need to do the same. I'm going to check to make sure that my answer makes sense. 3 with an exponent of 8 divided by 9.85 with an exponent of 7. That should give me almost no exponent, and in fact it does. And I'm going to round the 3.04 up to 3.05, and that is meters. Okay. It's a pretty large value, and that would be our answer there. Okay, so we have used the speed equation, right? We have used this equation here to solve for frequency when we're given the wavelength, and we solved for the wavelength when we're given the frequency, because we always knew the speed was constant. We said that the frequency is equal to the speed divided by the wavelength, and the wavelength is equal to the speed divided by the frequency. This was the constant, 3.00 times 10 to the 8th meters per second. Both times, I'm just reviewing. We have one more equation to look at, and this is whatever was given, and it had to be in meters. And if we divide those, we would have the frequency. This is what was given, and it has to be in hertz which is a per second, not a kilohertz, a megahertz, but a hertz, which is a per second, okay? And that is how we would get the wavelength. Now, that explains light as a wave, all right? That explains light as a wave. We could talk about its wavelengths and its frequencies. Now we're going to talk about light as a particle, okay? And light is considered a particle. I'm going to come down here, kind of elaborate. How do we talk about light as a particle? Well, let's talk about light like this. Light is electrons moving. It's produced when, all right? Produced when electrons are moving. From higher, oh gosh, from outer energy levels to lower energy levels. Or let's write energy levels closer to the nucleus. I don't want to go too far. Okay. Well, without trying to make this too confusing, here's our nucleus. We'll imagine this is our first energy level. This is our second. This is our third. It's almost like a ladder, right? And what we know is when we climb up a ladder or when we climb down a ladder, we can step here, or we can step here, or we can step here or here. But what we know that we cannot do, is we cannot step here or here or here or here, right? So we have to step on the rings of the ladder. Well, in the same way, our electrons can be here or here or here or here, so on. What they cannot do is locate the region. Oops, let me get a different color. They cannot locate the region in here, okay? They have to be on the energy level, all right? And in order to get from one energy level to another, they have to possess the perfect amount of energy. No more, no less. So to get them an electron from here to here, it needs to gain a multiple of HV. And I'm going to write, remember that V is the same as F. So H times the frequency. And we'll leave it at, I'm going to write H. Oops, that's too much undoing there. So let me get my eraser and see if I can just get a little bit erased. Okay, a little bit erased. Okay, and we're going to call this times HF, right? F for frequency. I'll tell you about H in a minute. In order to get to here, we have a multiple, some number, times HF, okay? In order to get from here to here, it's some multiple of HF. So what that means, guys, is electrons can either have this amount of energy, this amount of energy, this amount of energy, or this amount of energy. And they can release light that has the amount of energy that is the difference between either the difference between these two wavelengths or these two not wavelengths, these two levels, energy levels, or maybe they can release light that has this much energy, right? But they can't release light that has the energy in between. It's always a whole number multiple. Now, what that means is the energy of the photon, we're almost done here, which is a piece of light, okay, is equal to H times F. Okay, so it's our let. Well, we're going to say E is for energy of a photon, right? What is a photon? It is a piece of light. It is measured in joules, which is abbreviated J. Okay, H is Planck's constant. And F, again, is your frequency. So we could call it that upside down Z or V if we wanted to. All right. Now you see the word constant. That means this value doesn't change. It is found by Max Planck, a scientist of quantum physics, quantum mechanics. The value is 6.626 times 10 to the negative 34th. That is a J dot S. And your frequency here must be measured in per seconds, which is a hertz, which is a per second. Okay? So let's look at an example here. What is the energy of a photon with a frequency of, let me think real quick. Trying to get a number that makes sense. I'll just make it up. 7.98 times 10 to the 14th hertz. Question mark. So energy equals question mark. Frequency equals 7.98 times 10 to the 14th hertz. Okay, well, I know that E equals HV. Oops, and we're making that an F. So I told you, I always use it, V. I thought F might be easier for you. Okay, well, H is 6.626 times 10 to the negative 34th. J dot S. Frequency is given to us here, and this is an appropriate unit, right? So I do not need to make a conversion. Yay, right? So I can just plug that number in as is because the units are, they are the hertz and my seconds are opposites, so they will cancel. And I will multiply these values. So I got my calculator and I say 6.626 second EE, negative 34 times 7.98 with an exponent of 14. I should have an exponent around negative 20, negative 19. So I probably didn't make a mistake in my calculator. I'm going to round this to 3 sig figs, 5.29 times 10 to the negative 19th. And my unit left over here is joules. All right, and that would be my answer. We need to do one more. Okay, so what is the energy of a photon with a wavelength of, and let's make that 534 clear. Sorry, let's make that, nope, sorry. Let's make that 900 nanometers, okay? So what is the energy? So E equals question mark with of a photon with a wavelength of, I know that energy is equal to Planck's constant times the frequency, and I know that frequency equals speed divided by the wavelength. So I'm going to have to do this first. I'm going to first have to find my frequency so that I can then find my energy. Okay, so that's last. First, second. And it's going to give me the answer, right? Because the answer here is energy. But in order to get the energy, I need the frequency. Remember, I know H. And I can get the frequency by using my, let's get a green here, wavelength, right? Okay. So I know that C is 3.00 times 10 to the 8th meters per second. And I know that my wavelength was given to me right here, right? There's my wavelength. Uh-oh, that's in nanometers. I must convert to meters, right? Because down here I have meters in my 3.00 times 10 to the 8th. So I'm going to erase this because I can. I'm going to fix that because I made it very messy. Okay. And I'm going to draw my T-chart. I'm going to convert nanometers to meters. Metric system. Meters are larger. 1 times 10 to the 9th times larger. I will divide and I will get 9 times 10 to the negative 7th meters. Notice I only kept my one significant figure. Okay. We are going to let our wavelengths and our frequencies determine our significant figures and make the assumption that this speed has no error. It's 3.00. Probably not always true, but that's what we will do. All right, to minimize questions about that. We will let the wavelength and the frequency given determine our sig figs and the answers, okay? So I'm going to take my wavelength that I just calculated in meters and put it down here with the correct sig figs. I'm going to divide these values, 3 with an exponent of 8, divided by 9 with an exponent of negative 7. And that's going to give me 3 with an exponent of 14. Meters cancel, and that's going to be per second. Okay. So a lot of information there. There are 2 equations. And what we're doing is we just talked about the dual nature of light. We talked about light as a wave that is continuous. We talked about light as a particle. It is discontinuous. Light has wavelengths and frequencies and energies related to them. Light photons always carry a particular amount of energy that are in whole number multiples of H, F, H, F, H, F, okay? We talked about how we can organize electromagnetic radiation based on its wavelengths and frequencies. We talked about the wavelength frequency, or rather the speed equation. We said that the speed is always the same. Oops, it's always this. We said the wavelength must be in meters, and the frequency must be in hertz, and that is a per second. And that when you write your answers down, they'll look like this because you're going to type them in. We talked about the fact that we could rearrange this equation here to solve for frequency and to solve for the wavelength. We then solved a problem where we were given the wavelength in nanometers and we were asked to solve for the frequency. And we first had to convert the nanometers to meters, plug it into our equation, divide, get the answer, round to the correct sig figs, and label it appropriately. We then had a problem that gave us the frequency in megahertz and asked us for the wavelength. We wrote down our equation that we would need. We plugged in the speed. We had to convert the megahertz to hertz because our frequency always has to be in hertz to plug it in. All right, this is F. Okay, it always has to be in hertz. We divided the speed by the frequency in hertz, and we ended up with our wavelength in meters, and we rounded to the correct number of sig figs and labeled it. We then talked about light as a particle. We said that light is given off when the electrons move. The amount, the energy of the light that's given off is related. It's either this, which is HV. It's either this, which is HV. It's either this, which is HV. Or maybe we went all the way from here to here, which would be multiple HVs combined. All right. And we said that we couldn't have any energy in between. It's got to fall on these particular energy levels. Okay. And we put an equation with that. It's the E equals HF or E equals HV, the energy equation. The energy is giving us the energy of a photon. The photon is a piece of light. H is a constant. It is always the same value. Frequency, once again, must be in measured in hertz, sorry. We looked at a question where they gave us a frequency in hertz and asked for the energy. So we used our energy equation. We plugged in H, which is always the same value. Our frequency, we did not need to convert it because the unit was appropriate. We multiplied, we got the answer, we rounded, and we put the appropriate label on there. We then had a question that asked for the energy, which I did not finish, of a photon with a wavelength of 900 meters. I did not even finish this problem. We said we need the energy. In order to get the energy, we need the frequency. Well, I don't have the frequency, but I have the wavelength. So I converted my wavelength in meters to nanometers. I converted my wavelength in nanometers to meters. I then plugged it into my equation and said that the frequency is equal to the speed divided by the wavelength in meters. That gives me a frequency of this. However, the question here was how much energy. So I now need to take my energy equation, which is HF, and take my energy. H is 6.626 times 10 to the negative 34th JS. And I need to multiply that by my frequency, which I just got, which is 3 times 10 to the 14th. And that goes there. When I multiply those, 6.626 second E negative 34 times 3 second E 14 equals, I get, and yes, that makes sense. Always ask, does it make sense? I look at my exponents and say, do they make sense? 1.99 times 10 to the negative 19th. S and my per S cancel. I'm left with joules. And I should only have two sig figs. I should only have one. So I'm going to round this to 2 times 10 to the negative 19th joules. Okay? Write down your questions. This is real. Okay, we got to do this. All right? I'm going to stop, share, do the practice. All right, do the practice, write down your questions, we'll check them. Okay.